Hello, we are now live from the University of Hull. Welcome everyone to our virtual Pint of Science event. My name is Kiwi Newson and I'm a first year PhD student studying medical physics, and I will be your host for the evening. With my background being medical physics, I don't know much about space, so I'm just as excited as you are to find out more about today's topic of exploring the cosmos from atoms to galaxies. Our speakers today are made up of three inspiring women, which I've worked with for the past few years in our Changing Face of Physics campaign to increase diversity and women in physics. Our schedule for the evening starts with Born from Stars, the Origin of Chemical Elements, a talk given by Kate Womack. And then we have Leah Cox talking about turning back the cosmic clock. And then for our final speaker of the night, we have Emily Shelton looking at the social network connecting galaxies in the cosmic web. Throughout the evening, please take full advantage of our comment section where we can see all of your questions and comments, which we'll use at the end for our Q&A session, where we'll bring back all the speakers to answer as many questions as possible, whether that's about their university life or whether that's their current areas of research. If you could indicate the name of the speaker you wish to ask a question to, that would be really helpful for us too. And if I could also ask everyone to fill in the short survey during this to get some feedback, that would be greatly appreciated. This enters you into a prize draw where you can win one of our fantastic Pint of Science t-shirts or even a pint glass. This is found in the link in the description just below. So if you just pop an emoji maybe after you've completed that, that'd be real great. So you could just pop an emoji in the comments so I can just keep an eye on that. So without further ado, let's introduce our first speaker of the night, Kate Womack. Hi, Kate. Kate is a Master's Bioresearch student with an interest in the origins of chemical elements, specifically focusing on the production of heavy elements in low-mass stars. She completed her undergraduate at the University of Hull, and as a Hull girl, born and bred, she is a point of her pride to have her graduated from her home university. She therefore likes nothing more than to tell everyone how brilliant Chip Spice is and how she can't believe the rest of the country doesn't use the word 10 foot. Kate also works at Hull Gin School part-time, so in the evenings you'll probably find her with a gin on the go and an embroidery project in her hand. But as much as she could waffle on about Hull and gin all night today, she is here to talk to you about stellar origins of chemical elements. So over to you, Kate.
Thanks, Kiri. And hi everyone, I'm so excited to be able to talk to you today here at Pint of Science 2021. And I am here to give you a whistle-stop tour of the origins of the chemical elements. So let's get started. And I'm going to start here, where all good talks should start, with two inspirational quote posters that I found on Pinterest. And this is the kind of classic, famous, "We are made of star stuff" Carl Sagan quote. And though it kind of has been taken over a little bit by the Facebook meme pages of the world, it still rings entirely true. Every single element, every single atom that makes up every single thing on Earth, you know, from the desk that I'm sat at, to the laptop you're watching me on, to the person sitting next to you, started its life in a star. And I think there's a lot of things in astronomy and astrophysics that can make a person feel quite small. And this is the one that really does it for me. But now, if I was being really clever, I'd pop this next graphic on and just leave for the next 9 minutes, because this basically sums up everything that I want to talk to you about today. And I'm sure most of you will recognise this as the periodic table of the elements. I'm sure you will have seen this throughout your life, but maybe not coloured in quite this same way, because in this case, every single element has been given a colour based on the kind of event or star that makes it. So you can see that you've got the hydrogen and the helium made from the Big Bang. And then you've got kind of everything coming up to iron and just a little bit beyond, made in exploding massive stars and exploding white dwarfs, otherwise known as various types of supernova. And then you've got everything from strontium up to uranium, made in either major neutron stars or dying low mass stars. And it's those kind of heavier elements that are really the focus of my work. But tonight we're going to start with the exploding stuff, because everyone loves an explosion. That's why action movies do so well. So let's start here with core collapse supernova, otherwise known as exploding massive stars, otherwise known as type 2 supernova. 3 different names, essentially all the same thing. And this is one here. This is Cassiopeia A. And these tend to be stars with masses initially greater than about 8 times the mass of our sun. So these are really huge stars. And when you have stars this big, you get really short lifetimes. I'm sure you will have heard the phrase before, live fast, die young. Well, that's exactly what these stars do. They make a lot of elements via mainly charged particle reactions really quickly. And when they die, they release those into the universe and into the galaxy. And that's things like oxygen, neon, alpha elements, and some iron. And just as an aside, what I mean by an alpha element is any kind of light element that had to be made when the nucleus, so the middle of an atom, captured a helium, because sometimes we call helium an alpha particle. And then we can move on to our exploding white dwarfs, otherwise known as type 1a supernova. Now, you tend to find these in binary systems, so you'll have 2 stars orbiting around one another. And the white dwarf will use the force of its own gravitational pull to take material from its companion. And these stars are much lower mass and therefore much longer lived. You're looking at about 1 billion years or so, maybe a little bit shorter. And when these stars eventually die, they enrich the galaxy with things mostly iron, some of the intermediate mass elements, and the elements from titanium to zinc. And from titanium to zinc is what we call the iron group. So that's this group of elements here. And I'm going to take a second now to talk about iron, because iron is a bit of a stopping point when it comes to nuclear physics. And that's because it has something called maximum binding energy. And this sounds like quite a scary term, and I'm sure many of you might remember this from school science. So what this means is that the nucleus, so the center of the iron atom, is so positively charged that you can't do any kind of fusion or any kind of proton capture, any kind of charged particle reaction to try and add mass. You can't do, because it's like trying to add 2 north poles of a magnet. They're going to repel because of the positive charges. And so in order to make the heavier elements that we know exist, because we know things from cobalt and beyond do exist, we need a different process. We need something that can add mass without adding charge. We need a neutral particle. So we need neutrons. Clues very much in the name. And so to use these neutrons to make heavy elements, we do something called neutron capture, which is what I'm going to talk about now. Now, this next graphic looks pretty scary, but I promise you it's not. This is what we call the nuclide chart. And this places every single isotope that we know of as a function of its neutron and proton number. So however many neutrons it's got dictates where it goes along the bottom, and however many protons dictates where it goes up the side. Oops, I've gone a bit too far. I've given you a sneak peek of my next slide. And so this is essentially just to illustrate the 2 processes, or the 2 primary processes of neutron capture. And so we have the S process, and this stands for the slow neutron capture process. And so what this does, clues in the name, it slowly builds up heavy elements by capturing neutrons. So we start at something stable, and so we can capture, and it's stable again, so we capture. But when we get to something with a short half-life, we can decay a little bit, and then we capture some more, and so on. And it just kind of pootles along and builds up heavier and heavier elements. And then we have the R process, which stands for the rapid neutron capture process, which again does what it says on the tin. In this case, we have lots and lots and lots of neutrons. So the system just kind of goes, whoa, okay, loads of neutrons here. Let's make lots of heavy elements. And you'll notice here that I've got the S process in yellow to correspond with our low mass dying stars, and our R process in orange to correspond with our major neutron stars. So let's talk about them. So now we move on to our low mass dying stars, and we would call these AGB stars, which stands for asymptotic giant branch. And what that means is the star has gone through its hydrogen burning phase, so its main sequence, it's gone through its red giant phase, and now it's really starting to die. And these tend to have masses between 0.6 and 8 solar masses. And a range of masses creates a range of lifetimes. But the key with all of these is that they undergo the S process. And that means they make things like strontium, yttrium, zirconium, and barium. All of those yellow-coloured things from the periodic table graphic from before. And then we can move on to our major neutron stars. Now, these have been a really hot topic in the last few years, I'm sure you're all aware, because of that first detection by LIGO back in 2017. And that was really good for us because it's been very difficult for us to really narrow down a potential site for the art process, because we need something that's incredibly highly energetic to get the amount of neutrons required. And neutron star mergers really provide us with that. You know, these are very compact, very dense objects orbiting around each other. You know, you're cramming 1.4 times the mass of the sun into a space that's 20 kilometers in diameter. And these are the remaining cores of stars, which were previously 10 to 25 solar masses. And so when they undergo that highly energetic merger, we can make things like europium, platinum, and gold, you know, our precious metals. And in about 8 minutes, I've pretty much told you where almost every single element on this table originates from. But it's all well and good me saying, okay, well, arsenic comes from an exploding massive star, and osmium mainly comes from merging neutron stars. But how does it all get here? Well, 3 main ways. Number 1, the nebula the Earth was born in. You know, the Earth and the solar system is only around 4.5 billion years old, but the universe is 13 billion years old. So that's plenty of time for stars to have been born and die, enrich the galaxy with all of their elements. And so when the kind of gas and dust cloud that the Earth was formed in, you know, forms the solar system, all the elements that were around come with it. Our other way is meteors. So this here is a picture of the meteor that landed in March on someone's driveway in Gloucestershire. And if you think about the lifetime of the Earth, how many meteors will have landed and brought with them tiny grains of material within inside them that, you know, were around when the meteor was formed. And those grains of material have come from a dying star and then been brought to Earth. And the final way is winds. Now think about one of those huge core collapse supernova, and that exploding pushes out all sorts of elements into the galaxy. And you can bet that some of them are going to find their way here. And that pretty much brings me to the end of my talk today. I hope in this whistle-stop tour of the galaxy and of the universe that you have learned something about how elements are made. And I will thank you all and pass you back over to Kiri.
Thank you so much, Kate, for that talk. How cool is it that matter found on Earth today could have landed from a meteor billions of years ago?
Right, and it's so exciting because when those meteors land, we can take them to a lab and really analyse those grains and see if we can narrow down what processes might have made them and what stars they might have come from. So it's really awesome.
Oh, no way. Yeah, that was really cool. Thank you for that. Don't forget, if you've got any questions for Kate, simply pop them in the comments below for us to pick out later on. If you can maybe add a name just so we know who to ask, that would be really helpful as well. So now we're going to head over live to our Mars correspondent, Professor Brad Gibson, who's going to share with us a little bit about the current research surrounding Mars.
Great. Thanks very much, Kiri. I just want to say greetings to all from Jezero Crater, the current home of NASA's Perseverance rover and the Ingenuity helicopter. I thought about doing this talk outside, but having checked the weather out in the crater right now, decided it's a bit too chilly this evening. It's minus 82 degrees, so I think we'll give it a pass. There's also really strong winds, and in fact, there's strong winds on Mars almost all the time, whipping up dust almost all the time. There's dust everywhere, and it's not like the dust here on Earth. It's really nasty stuff. It's really highly carcinogenic, leads to cancer. So this is one of the issues that I'll come back to a bit later, that future colonizers of Mars are going to have to be extremely careful about. You can't let any dust into your suit or whatever sort of pressurized structure you might be living in. You can't traipse the dust in because it's really nasty stuff. But this is a really exciting time for Mars exploration. We've got 3 successful missions currently underway here. As I said, NASA's Perseverance rover is wandering around the crater. Why did they choose this particular crater? Well, because probably about 4 billion years ago, it was likely the home to a deep lake. And so one of its primary missions is to collect and store a large number of soil samples that will be later collected from as part of a future mission. The goal there is to answer that question we all want to know the answer to. Did life exist on Mars 4 billion years ago when there was water on the surface? And examining these soil samples will hopefully provide the definitive answer as to whether life did exist 4 billion years ago on Mars. I'll be back in 10 minutes or so to say a bit more about the challenges facing future colonizers of Mars and why it's likely that there isn't any life there now, even if there was 4 billion years ago. So back to you, Kiri.
Thanks for that, Brad. That was really interesting. So now we'll move on to our second speaker of the night, Leah Cox. Leah is a final year PhD student here at the University of Hull. Her research focuses on the galactic halo and galaxy evolution. Leah has engaged in a lot of outreach events that are aimed at encouraging women to follow their scientific interests and has also won 2 awards for her commitment to the department. Alongside university commitments, Leah likes to stay active by taking part in activities such as going to the gym, climbing, Brazilian Jiu-Jitsu and kickboxing, and she's also an aspiring astronaut. So for our second talk of the evening, Leah will now enlighten us to how we can use the elements in stars as cosmic clocks. Over to you.
Right, so thank you again for joining us today, and thank you, Kiri, for introducing me so nicely. And yes, I actually am an aspiring astronaut. Pretty cool, I know. I'm going to be talking to you about cosmic clocks and how we use certain abundances as a giveaway of how old a star is. So firstly, here's a brief overview of the contents of the talk. What is a cosmic clock? What is the purpose of one? And why do we use magnesium and iron as our markers for stellar age? I'll also show you a snippet of what I've been working on recently and the implications of this before discussing the future age dating stars. So what is a cosmic clock? Well, as we have just heard a fantastic talk from Kate on the formation of the elements of the universe, I can expand on this to discuss my topic. So by looking at the elements present in a star, we can estimate the age of that star based on how much of one element there is present compared to another element also present. So the amount of one thing compared to the amount of another will allow us to gain a deeper insight into how things form and perhaps give us clues as to why they form that way. So we know that it is the type 2 supernovae, the stars that like to live fast and die young, that eventually cause the formation of the majority of the alpha elements, and that the iron peak elements form in type 1a supernovae, which have much longer lifetimes than type 2. So we can then compare the elements that form in different environments and on different timescales. Hence why I'm looking at magnesium and comparing it with iron. So both magnesium and iron are found in massive and intermediate mass stars. What makes magnesium and iron also elements of choice is due to the fact that they're easily detected in the optical region using spectroscopy, which brings me on to my next point. So it's actually very difficult to initially tell how old a star is just from looking at it. So we all know that the sun is roughly 4.5 billion years old, but how can we actually age such an object just by looking at it? So for objects on Earth, we can use carbon dating to tell how old something is. But for stellar objects, we must use something else, and this is called spectroscopy. But what actually is spectroscopy? And how is it used for measuring the age of a star? So we can use telescopes to measure radiation from different regions of the electromagnetic spectrum. So for example, we can measure things like X-rays, radio waves, and of course, visible light. And we can also tell a lot about a star by using spectroscopy. So we can break down the chemical composition of the star, as well as being able to tell how hot it is and how luminous it is. So if you think about holding a glass prism up to a light and seeing the individual colours splitting up as the light exits the prism, this is essentially what happens when we are measuring the elements that are present in the star. So if you look at this image here on the right-hand side, you can see the light or the electromagnetic radiation, which is what it is, that is leaving the sun, and it is also passing through a prism. So the result of splitting up the wavelengths of radiation is the rainbow-coloured spectrum as shown next to the prism. So these black lines present on the resulting spectrum are what are known as absorption lines, and these actually represent the elements that are present in the star. So what I'm showing you now on the top line here, this is called an absorption spectrum. And again here, the black lines that you can see that are disrupting the rainbow of colours in the spectrum are showing you what is exactly getting absorbed by the star's outer atmosphere, otherwise known as the photosphere. So we know exactly which elements each line corresponds to, as we can recreate this experiment on Earth, but in reverse. So the image underneath shows an emission spectrum. So the lines that are present on the emission spectrum here essentially show us what happens when a gas gets excited and emits energy. So the coloured lines that show up on the emission spectrum actually kind of match and slot in to the missing lines that are present on the absorption spectrum. So therefore, if we think the element is something like carbon, for example, and the emission spectrum perfectly slots into the absorption spectrum, then ding ding, we've got a winner. So now we have a bit of background on what spectroscopy actually is and what the elements, where the elements magnesium and iron actually come from. So what can we actually do with these? So for one of my chapters of research, I have been investigating the role of magnesium versus iron as a marker for the age of stars. So the surface of a star that we see actually reflects what is occurring in the core. Certain elements will be present at the surface of a star during certain points of its lifetime. For example, the star will initially fuse hydrogen to helium, and then helium fuses to form heavier elements, and so on. As Kate has already told us, so we know all about that. So these elements can then make their way to the surface. This is when we can actually like see them, basically, with telescopes. So therefore, it is easier to tell if a star is actually beginning its life or about to explode. The intermediate in between is a bit more difficult. So by observing one element alone, we can tell how much of it there is present, but without having something that we can compare it to, it doesn't really serve much of a purpose alone. Like, yeah, great, we've got loads of that, but what does it mean? So therefore, we must pick an element that we can actually easily compare it to. So by choosing an element that has formed on a shorter time scale in the more abundantly exploding type 2 supernovae versus an element that has formed on a longer time scale, in the less abundantly exploding type 1a supernovae, this will give us an insight as to how old the star probably is. So I have been working with a Milky Way-like simulations. The simulation I'm using here for this project is called Selene. So if I refer to Selene, just know that it is basically just a Milky Way-like galaxy. If you look at the image on the left-hand side, it looks a bit confusing right now. I understand that. But each thing on that plot basically represents data about the Milky Way, whether it's been gathered by observations with telescopes or if it's simulated, using computer code. So this plot here shows the magnesium over iron on the vertical y-axis, and then we've got the ages of the stars plotted on the x-axis, the horizontal axis. So the black dots scattered across the plot represent Selene, our galaxy simulation. And the multicolored crosses represent the observational data that people have gathered through telescopes by using spectroscopy. So finally, we've got 4 different colored lines, and these each represent galactic chemical evolution codes, and these all have basically different initial rates of type 1a explosions. So the green, blue, and the red lines are from something that's called Omega Plus, and the orange line is a different chemical evolution code entirely. So we do actually have 3 approaches to modeling the Milky Way here, basically, and the observational data that we obviously want to compare to. So I know that was a mouthful, but if you remember that the black dots are from simulated data and the crosses are data from observations, and then the lines are essentially different chemical evolution codes that vary the rate at which type 1a supernovae explode, that might make it a bit easier to think about. I do understand that it is quite confusing just to look at that though. So the type 1a supernova rate ultimately gives away if the star is going to be old or young, as on average, a type 1a supernova in a binary star system will take longer before it eventually explodes and releases heavier elements such as iron into the surrounding interstellar medium. So therefore, by varying the initial supernova 1a prescription, sorry, saying supernova 1a is a massive mouthful, we get to see what events play out depending on if the iron is released earlier or later into the surrounding medium. So what does this actually mean? So we can see from the image that it is difficult to perfectly model the Milky Way galaxy. It's actually, really hard. So then if that's hard alone, then it is obviously has the implication that it's really, really difficult, even more difficult to measure the age of a star. So by using different approaches to modeling the Milky Way galaxy, we sort of get to see what works and what doesn't work when we try to match the observational data. We need to match the observational data as it's important to have something to compare it to, so we know if our model is going in the right direction or not. And so it also gives us some predictive power actually for things we don't currently have observational data for. So for the work I have just shown you, I have been altering the rate at which type 1a supernova explode, and thus playing around with the rate that iron actually enriches the interstellar medium, like the surrounding gas. And Kate has actually been working on this with me, so she should know about this as well, which is good. So basically, the later on that we assume that these stars explode, the more time we have to wait for greater amounts of iron to be present. And the earlier on we assume they explode, the more quickly we obtain greater amounts of iron. So the main points to take away from what I've shown you are that for the Selene simulation I'm using, it matches the observational data well. And so we can say that using the mg over Fe value calculated in the simulation matches with how old we would expect a star to be in observations. So the older the star is, the less iron it has. And the younger the star is, the more iron it has. And that is the generalization. So this makes sense as it would take time for heavier elements to be produced, especially if these stars aren't exploding as frequently as well. So for example, for some reason, if you ever overhear somebody saying that a particular star has a high mg over Fe value, you would then know that they were referring to an old star, as there would be much more magnesium present than iron, as not enough type 1As would have exploded yet to enrich the interstellar medium. So we can also see in the image that by varying the rate at which type 1As explode, the slope also varies. So it would appear that from the chemical evolution codes, the red line actually best matches the observational data. I would say so. And this red line actually is just showing that the type 1a supernova rate is delayed. So therefore, for this data, it looks like a delayed explosion rate represents what is seen in the actual Milky Way, like that we observe with telescopes. So it's basically just saying that, you know, they don't kind of explode as the galaxies form, and, you know, we're going to wait a bit and then everything's going to come in, and that's when we get the iron. So is it, we call this a delayed, a delayed explosion rate, basically. So knowing all of this and how difficult it is to age date a star, well, where do we go from here? There are actually missions that send satellites to space to observe large host stars in the search for exoplanets. As the host stars are being closely monitored, the satellites can constantly measure the small changes that appear on the surface. And as we know, the small changes reflect what is actually going on in the core of the star. This will give us a more accurate idea of how old the stars actually are. So hopefully by being able to constantly sort of monitor these stars with these satellites, this should be a better improvement than what we already have. Obviously, as we know, easy to measure kind of really young stars or really, really old stars, but that intermediate gap, you know, we need to find a better way to sort of monitor that. So that's all from me and our 10-minute sort of how-to lesson on using elements to age date stars. I hope that was interesting, and maybe you learned something you didn't already know from that. And now I'll pass back over to Kiri.
Thanks so much for that insight, Leah. It was really interesting. Is it then possible to use any element to tell the age of stars?
Oh yeah, you can absolutely use other elements. I just chose magnesium and iron as they're easier to obtain data for, but basically if you use anything, like any element that's formed on a shorter time scale and compare it with an element that's formed on a longer time scale, like you're pretty good to go.
Oh, no way. Thank you for that. Again, for any questions you may have for Leah, pop them in the comments below because I can see them throughout. Definitely try and indicate that it is for Leah though, so I can just take note of that. So before our final talk of the evening, let's check back in with Brad on Mars and see what he has to say.
Thanks, Carrie. I ended my initial 2-minute segment. I talked about the search for life that may have existed on Mars 4 billion years ago. Again, this one of the primary goals that NASA's Perseverance mission was established to try to answer. And so one of the most common questions I do get asked is there life on Mars now? As I said, there's a good chance it was on Mars 4 billion years ago. And this is a really exciting question that will get answered over the next few years once we get the soil samples analyzed. Unfortunately, the conditions now on Mars are much more hostile than they were back 4 billion years ago. I mentioned that cancer-causing dust that surrounds you all the time that's here on Mars, but there's more bad news on the soil front. It's ridiculously toxic. It's laced with what's called perchlorates, kind of like a chlorine. If you've gone swimming and you've had a little bit of chlorine in your eyes, you know how much that hurts. These perchlorate salts are lethal to even the hardiest plants and microbial life forms. So it would be very unlikely anything could survive in the soil on Mars currently. Now, the nice thing about it is if you can't find liquid water there, though, you have a good chance of dissolving away these perchlorates that make the soil so lethal. So in terms of long-term colonization, we're going to need liquid water to filter out the perchlorates that make that soil so toxic. And one of the other real killers for life on Mars now is that there's no atmosphere to speak of, really. And that's just down to the fact that Mars doesn't have a magnetic field, unlike Earth. Earth is just a big giant bar magnet, and that allows us to see super cool aurora borealis and australis. But more importantly, it shields the atmosphere from being stripped away by high energy particles that come from the sun. Not having that shield on Mars means there's no atmosphere. It also means the surface radiation is 1,000 times more damaging to DNA, for example, than it is here on the surface of Earth. So any future colonies will have to live deep underground or in sort of pressurized meter-thick containers to keep themselves protected from this radiation. So, combined with all those things together makes it very unlikely that life could exist there today. Happy to be proven wrong, but I think that's where things are looking now. But answering the question whether life was there 4 billion years ago, really exciting times ahead for Mars exploration right now, even if the future of Mars colonies looks a lot more challenging. Back to you, Kiri.
Thanks for that, Brad. Some great information on Mars there. So now on to our final talk of the evening, Emily Shelton. Emily is a Masters by Research student who focuses on the large-scale structure and what this means for the fate of the universe. She completed her undergraduate degree at the University of Hull. Emily comes from a town called Mansfield in Nottinghamshire, and she grew up as a member of the local taekwondo club with her sister. She now enjoys bouldering and local climbing at a local climbing gym, and tries to find any reason to climb outside in the Peak District, providing it's not too cold. She's now going to talk to you guys about the clusters of galaxies and how we can use it to find things out about the universe.
Thank you very much for the introduction, Kiri. Hi everyone, I'm Emily and welcome to my talk about the Galactic Social Network. So this evening I'll be talking about the universe as if galaxies were friends with each other. So in this presentation, I will set the scene by talking, first of all, what the galaxy and what the universe looks like, so that we can all see what we're working with. Then I'll go over clusters of galaxies, what they are, and what exactly I mean when I say that galaxies are friends with each other. And then I'll explain what this means in terms of science and research, and then I will describe how we can use this information to discover the fate of the universe. So let's get started. So let's start small, shall we? I could start as small as the atoms that Kate taught us about earlier, but that would be too small. So instead, I'll kind of use the stars that Leah uses in her research as the start of our cosmic ladder. So for step one, we can start right here on Earth and with our star, the sun, which forms a part of our solar system. So going up a step, if we put lots and lots, and now I'm talking like millions here, of solar systems together, we form a galaxy. If we were to put many galaxies together, we create a cluster of galaxies. And taking another step up, we can put many clusters of galaxies together to form what is called a filament. Now, in between these galaxies and filaments and all that stuff is an absence of stuff that we call voids. And these voids contain nothing. So to show you what this looks like, I have here on the right-hand side of the screen, a picture that some of you may have seen before of what is called the Millennium Run simulation. So if you can follow my description, we can see these bright yellow and pink spots in the picture, and those are clusters of galaxies and filaments, just very, very far away. All these dark and purple black regions contain much less stuff, if you will, and that's where the voids are. So also in this image, we can see a small scale bar that says 31.25 MPC over H, which might not mean much at the moment, so I can translate that for you now. So 31.25 megaparsecs, which is what the MPC means, is a distance, and 1 parsec is 30 million billion meters. And in this picture, that white line is 30 million of those. That's a lot of zeros, just for a sense of the scale of what we're talking about here. So the universe is kind of described as a cosmic web, like in the title of my talk, because galaxies and filaments and such make a kind of web by weaving in and out of each other and crossing over and overlapping and frankly making a right mess. So this is also analogous to a sponge, as we can see in the picture here. It kind of has a bit of a similar structure because the material of the sponge kind of interconnects and weaves and has holes and gaps, sort of like the universe. So I've been describing galaxies as friends. Well, what does that mean? They can't actually be friends, can they? Well, if we were in a pub like we were supposed to be, I'd tell you guys that if we were all galaxies and everyone whose shoulders you could reach out and put your hands on were your friends, and if we were all sat close enough together, we would be able to put a hands-on shoulders kind of path from one side of the room to the other. And like that, we would be able to form a filament that spanned the length of the room. So in science terms, this means that we would have percolated. So in the universe, if galaxies and clusters are within a certain proximity to each other, if they are within some radius, they can connect and form a path that spans from one side of the picture to the other. So in the Millennium Run picture I showed you earlier and how we have on screen now, we can see this so-called percolation here, where if we start on the left-hand side, we can follow the white arrows that I've added to the picture to kind of follow the yellow and pink kind of dots and paths across the screen. all the way to the bottom right-hand side. And all of those galaxies and clusters and filaments are all connected. This is just one example, but as I'm sure you can see just by looking at the picture, there are so many possible paths that we could have taken to go from one side of the picture to the other. And we can kind of do something similar with the sponge as well. So kind of what does that mean? Now that we know that galaxies can make friends with each other, what does this mean? So it is this structure of galaxies and the filaments that they form that are the secrets, or they're the key to the secrets of how the universe formed and evolved into what it is today. And it is this structure, these galaxies and filaments, that tell us about gravity, tell us about density, how the galaxies formed, and how they created the elements that make us who we are today, like what Kate and Leah spoke about previously. So researchers told us that the distributions and relationships between the clusters and galaxies and the large voids give us details about the initial fluctuations that caused the universe that we see and experience today. We can use the trends that we see from the past to trace into the future and predict what the universe will look like, and eventually the fate of the universe. So we can see the past of our universe by literally looking at it through surveys, telescopes, images that we have taken from very, very far away. And we can look at the percolation and how the galaxies interact with each other in the early universe and all throughout time. So by seeing how the universe has evolved over the past several billion years, we can project this path of evolution and see how it will look in a few more years' time. So in summary, by finding out how galaxies connect and interact, we can roll back the clock and sneak a peek into the universe's past to find out how everything came to be how it is today and how it might look in the future. So that is all from me today. Thank you very much. Back to Kiri.
Thank you, Emily. That was brilliant. Isn't it great how we can find out so much about the past? How far are we talking?
So we can go back as far as we can see through those telescopes and with the surveys. So that'll be almost as far back as the Big Bang, within a few million years.
No way. Oh, well, thank you for that. And also thanks to those of you completing the survey and letting us know in the comments. If you haven't yet had chance, you can find it in the description below to enter into the prize draw. This leads us onto our Q&A section of the evening, where we will go through some questions from the comment section. Feel free to keep asking questions as we go, and hopefully we'll pick one that you've posted. So let's welcome back all of our speakers into the room. Hello. Hi, guys.
Hiya.
So for our first question, we'll just pop them up on the screen so everyone can see them as well. Apologies. So I've got a question here we've got a question from Kevin Ham. Are elements made randomly? If so, why rare elements like gold found in lumps?
Okay, so this is probably a question for me. And to be honest, the answer is a bit too much of the geochemistry side of things for me to be able to give a good answer on this one, really. So sorry, Kevin, this is not my area of expertise whatsoever.
No, that's no problem. So we'll move on to the next question. So we have another question here from also Jimmy, I believe. Oh no, we had Kevin before, apologies. So Leah, why are satellites being sent into our outer space as opposed to just into orbit around Earth?
Yes, that's a really good question, to be honest. There are satellites orbiting Earth anyway, but I think for the purpose of searching for exoplanets, like, you know, kind of putting more satellites around the Earth is a bit pointless. So if we're looking for other planets, you know, outside of our solar system, we need to be looking at other host stars. So obviously our host star is the sun. There's not really much more, well, not really much more point in looking at it. I mean, there probably is, but I mean, you know, trying to search for other sort of solar systems, you know, that's why we kind of send them into outer space. So we already do, basically, we do have satellites orbiting Earth, but we are looking for new sort of solar systems and new Earth-like planets.
That's really brilliant. Thank you for that answer. So we'll move on to the next question. So we have Robert Baker. Are there elements that don't exist on Earth that you have found?
Okay, so this also kind of ties in quite nicely with a question I think I saw about the kind of grey points that I was showing on my periodic table. So basically those two grey points are elements where no stable isotopes exist. And so even though they would have been present on Earth at some point, any kind of presence of those, I think it's technetium and promethium, are no longer there. They decayed a long time ago. But we can still detect those elements in stars. And this gives me a really good opportunity to talk about technetium, because technetium is a really important element when we talk about the S process. Because if we see that technetium in a star, we know that the S process is currently happening at the minute we observe it, because technetium has no stable isotopes. So if we see it, we know it hasn't decayed yet. But yes, there are elements that, we don't find on Earth, but we can still find them in stars.
Yeah, that's brilliant. So our next question is for Emily. So we've got from Lara, would you be able to give any insight on why this web-like structure occurs, and also why galaxies form from this net of voids and filaments instead of just uniformly expanding out?
So I think this comes from initially the Big Bang. Everything kind of explodes outwards, and then I think things will kind of all clump together a bit and kind of form slightly more denser areas with a bit more mass, and which will obviously, because gravity is a thing, more things will become attracted to that. And then over time, things will just kind of clump together and form kind of little balls of extra bit of gravity where more things will come in. And given enough time and space, big structures like that will form because of gravity and the way that works.
Yeah, that's brilliant. Thank you. Cheers. So the next question is for Leah. So Leah, if absorption and emission spectra happen when an electron jumps from one shell to another, then how can 4 electron shells, S, P, and D, and F, account for 92 different elements?
That's actually a really interesting question that I honestly don't have the answer to. I don't think my knowledge in that particular area is sufficient enough to actually give you a good answer, but that is something I could look at. And if you are interested, you could drop me an email and I'm sure I could try and give you a good explanation then. But you've actually got me thinking now, if I'm honest. Apologies.
No, that's brilliant. No, it's fine. I mean, I'm going to be honest, I couldn't answer any of these questions. So you're all doing
we're all
great
learning
anyway.
Together, right?
Yeah. So our next question is from Tales. So we've got a question for Emily. So will the universe expand to a point where all other galaxies are out of our vision, both with and without telescopes? And thank you.
Thank you for the question, Tales. I think that depends on what kind of universe that we live in. But if we live in one of these universes where it will expand forever, eventually, yes, all galaxies will just kind of expand that aren't within our local group, as far as I'm aware. Anyone who knows more about local clusters, Leah, might want to correct me on that. But as far as I'm aware, everything else will just expand forever away and we won't be able to see that.
Oh, thank you. So our next question is for Kate from Michelle. So we've got, how are the neutrons for neutron captures produced?
Okay, so this is a really good question. And this is something that I actually spend a lot of time looking at. So the way neutrons are produced depends on the mass and also the metallicity of the star. But for the objects that I look at, which are low mass, low metallicity AGB stars, what you have is a structure where you have the central core, and then around that you have a helium burning shell. Around the outside you have a hydrogen burning shell, and in the middle you have what we call the convective intershell region, which basically means as that region convects, it drags down protons from the hydrogen burning shell. Those protons add onto a carbon-12 to make carbon-13. That carbon-13 captures a helium And in doing so, that makes oxygen 16 and neutrons. So in the stars I study, it's all about that convection dragging down the protons, and then that kicks off a series of nuclear reactions that then give us the neutrons to make our heavy elements.
Well, thank you for that. So the next question we've got is for Leah. So Phil says, Leah, what makes you want to be an astronaut? Which I think is a really good question.
I mean, I think it's just super cool, right? Do you know what? I just honestly think it would be like a really, really fun thing to do. And I think it would just be so cool to just be able to go out like into outer space and like look down on the Earth. Do you know what I mean? Like, because you don't really know what it looks like from your own eyes. And I just think that would be such like an interesting thing to be able to see. I don't know. I just quite like a challenge, quite like the idea of a challenge and doing something just mental, really.
Yeah, no, I really like that. It's really interesting. So I think that's maybe, so we've got one more question here as well. So from Chloe, we've got, what do you think the future holds for the universe? And that's for you, Emily.
Thank you for the question, Chloe. I think that is quite a difficult question to answer. What does the universe hold? I think it will just expand for a very long time, way beyond all of our lifetimes. And I think, I don't know what I think.
What will the structure look like? What do you think?
What will the structure look like? I think, yeah, I think it will just continue to kind of branch out further and further into the universe. I think maybe over the kind of large scales of time, kind of like what Talis was asking earlier, I think eventually the filaments may kind of stretch quite thin, kind of like chewing gum maybe. And I think it will just kind of branch out and quite thin, but it'll just get lots and lots of bigger. Lots.
Funny analogy. I like that, like chewing gum.
Oh, thank you. So we've got one last question, I believe. So it's for all of us. What made you choose science? You're an inspiration to women everywhere. Oh, thank you. That was really great. Who wants to start?
I'll kick off if that's all right. Yeah. So for me, I think I kind of have my parents to thank, probably. I think when I was little, I kind of showed a really active interest in science, even from primary school. And they were the ones who kind of talked to me about it and encouraged that interest that I had about, even just from like year 2 and like push and pull and, you know, just like the little things you learn. And I think from there, the encouragement from parents and teachers and university is just, it's really, I think that's what's got me where I am.
No, that's a really good.
I'll be next. Yes.
Yeah, go on then.
I don't know really. Like, I think I've always quite liked knowing how things work anyway. Like, I'm kind of like a why person. I don't know. I just really enjoyed science in secondary school, and I think it was started when I was starting to do like astronomy in like year 9, like pre-GCSE. I really thought it was interesting, and I actually realized I was really good at physics. So I think I just kind of held on to that. I was like, you know what, I'm actually really good at this. This is super interesting. I'm going to carry on. And you know what, I'm doing a PhD now. So here I am.
And then we'll go to Emily.
Yeah, I think kind of growing up, I've always thought that space was really cool. I thought it was just absolutely fascinating, the thought of kind of what's out there. And I've always loved it all throughout school. I was really good that it wasn't a bigger part of like science and like GCSE science and even A-level science. There was about 10 pages in the textbook. I was devastated. So I decided to take it at uni, and then I found out that it was only 1 module a year. But I've always just thought that it was such a cool thing to just listen to. And I thought, I want to listen to this for 20 hours a week at university. And I think it's really cool. It's really fun to talk about. Everyone's interested in it.
Yeah, 100%. To be honest, my answer is pretty much very similar to everyone else's. Like, I found science probably the most interesting subject at school. Probably found it the most engaging and enjoyable lesson to attend. That could be maybe due to the teachers or the people around me potentially as well, maybe helping me enjoy it a bit more than other subjects. But yeah, definitely had my mind set on doing something to do with medical physics. So I'm really happy that I've managed to get a PhD position to actually be able to do that, which is really great. But unfortunately, that's all we've got time for question-wise today. So I'm just going to thank you all again for you three for doing your talks and things. So thank you very much. And thank you. So don't forget to also fill out the survey in the description box to enter into the prize draw just one more time. And thanks to all our speakers tonight. It was really interesting, and I hope you've all enjoyed it as much as I have. If anyone wishes to rewatch or catch up on this or any other Pint of Science events, they can all be found on the YouTube page. And you can also mention us on Twitter with the @PintOfScience using the hashtag Pint21. So if you have any further questions, we'll be keeping an eye out on both of these platforms. So hopefully we can answer your questions in the future. So that's all we've got time for today. And again, thanks for coming. And for those joining another show after this, enjoy that. So thank you very much and goodbye.